Okay. All right, guys. So we have already talked about this second messenger system. And we said that when we use the second messenger system, we use it when we are unable as first messengers to traverse and cross the membrane because of the chemistry. So if you are hydrophobic, you are able to cross the membrane. If you are hydrophilic, then you need a second messenger. And this example, it's not too early to get yourself used to it because we're going to see it a lot. And that is a messenger such as epinephrine would bind on the outside. So say no more, you already know that because it needs to bind on the outside, and on its behalf, another second messenger exerts the effect. And here the second messenger is the cyclic AMP. So we need to generate a second messenger, and the second messenger will activate an inactive kinase, and the activated kinase will now activate the inactive enzyme, and then we will have various metabolic effects. So now let's talk more about this glycocalyx that we said is like the barcode, and this is what makes the cells different. So the glycocalyx are carbohydrate moieties of glycoproteins and glycolipids that are found at the surface of the plasma membrane, and they are unique in everyone except identical twins. So the functions of the glycocalyx are protection, immunity to infection, and they are there for defense against cancer, transplant compatibility, cell adhesion, fertilization, and embryonic development. We just need to understand what the glycocalyx is. Okay? Then we are now going to talk about extensions that are on the cell surface. One of those is the microvilli. These are extensions about 1 to 2 micrometers of the membrane that serve to increase the surface area. And they provide about 15 to 40 times more surface area to the cells that have them. So microvilli are best developed in the intestine, in the small intestine, because that is where you have maximal absorption taking place. We're trying to absorb the nutrients that we have taken into our body from the digestive system into the circulatory system. So now we have broken down the food mechanically, and then we digested it chemically, whether from polymer we go to disaccharide, then we go to monosaccharide, and then we go from a protein into a peptide, and then we go from fats into a triacylglycerol, free fatty acids, and glycerol. After I broke them down, then I can shuttle them into the cell. But before that, I need to absorb. I need to absorb everything into the blood so I can deliver it to the tissue so I can get ATP. So microvilli, it's very important for you to remember, where do we find microvilli and why are they important and useful? They are important because they increase surface area, and I increase surface area to maximize the process of absorption. So some absorptive cells, they are very dense and appear as fringe, and they are called brush border. So the brush border is found in the intestines. So some microvilli contain actin filaments that are tugged toward the center of the cell to milk absorbed contents into the cell. So that shows you the glycocalyx, and these are, you see the microvilli, they are like evaginations. They are like evaginations, and they have actin microfilaments, and you see the microfilaments, and these are the evaginations. These are your microvilli. We also have cilia. They are like microvilli, but they are also different. Cilia are hair-like processes, 7 to 10 micrometers long, and they are single, non-motile primary cilia. They are found on nearly every cell. and serves as the antenna for monitoring nearby conditions. So they help with the balance in the inner ear, and they are also important for light detection with the rhodopsin, the rods and the cones of the eyes, and we're gonna get to that when we are doing our nervous system. So so there are multiple non-motile cilia found on the sensory cells of the nose, and they are very important processes. They are very important non-motile projections that have significant functions in the inner ear, as we said, and in the retina. So the motile cilia are less widespread. They are found in the respiratory tract. They are found in the uterine tubes, the ventricles of the brain, and the ducts of the testes. So the powder stroke is followed by recovery stroke. So you see that they are moving. They're not like the microvilli. Microvilli, they are not hair-like, but they can move, but they cannot move. But the cilia, they power stroke, and they are able to move, and they are able to sweep things down. So you can speculate, where can we usually find these cilia? We find them in your nose, very good, and we find them also in the respiratory tract to bring down the air and to obstruct any debris and remove it, propel it upward, prevent it from going downward to obstruct my alveoli. Okay, so the cilia move within saline layer at the cell surface. So the mucus floats atop this layer, and the structure cilium, the structure is known as the cilium, and the axoneme is the core of the motile cilium consisting of microtubules. The axoneme is 9 plus 2 structures, so there are always 2 central macrotubules surrounded by a ring of 9 pairs. So the ring of 9 pairs anchors the cilium to the cell as part of the basal body. And the dynein arms crawl up adjacent microtubules and bending the cilium using the energy of ATP. So that shows us the cilia. That's the basal body, and that's the shaft of the cilium, and that is the plasma membrane. And that shows us the 2 plus 9 pairs. There's 1 pair, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9 around it. So these are the dynein arms, and these are the central tubules, and these are the peripheral tubules. So central 2 and peripheral 9. So now that's the ciliary action. It shows you how the cilia, due to their dynein arms and the microtubules. So in the microvilli, we had microfilaments. You see, we had microfilaments in the microvilli, but in cilia we don't have microfilaments. We have microtubules. So these are like the exam questions. So that's what you're going to be asked. Even though cilia and microvilli are important because they are structures that are evaginations and they are important for movement, but how are they different? The difference would be structurally, because the microvilli are important for surface area, to increase surface area, and they have microfilaments, while the cilia are important for movement. They're not important for surface area, and they do not have microfilament. Cilia have microtubules. Very good. Very good. Okay, you see that's the powder stroke. So it strokes the powder stroke to move the food down or move the mucus down, and then the recovery stroke is to realign back to the initial position. Okay, so what is cystic fibrosis? Cystic fibrosis is a hereditary disease in which cells make chloride pumps but fail to install them in the plasma membrane. So that means we will have problems with the permeability of chloride. So chloride can never enter because the channels are there, but they cannot be plugged into the cell plasma membrane. So they will be on the outside. So that means chloride will always be a lot on the outside. That's how back in the day they used to find out if a patient has cystic fibrosis. The doctor would taste the skin of the patient. If it's salty, that means that this patient has cystic fibrosis. Yeah. Oh, they used to taste urine. What are you talking about? Even for diabetes back in the day, or they used to also they used to yeah they used to like put they used to put the urine on the floor and come back later if there is ants. That means there is sugar in your urine. So they used to do these things back in the day. But that is just to show you. I mean that's amazing how far a medical doctor would go for the well-being and health of their patient. I mean, yeah, they had no choice. Yeah, they really had no choice. Things got better, but yeah, doctors always underrepresented. And yeah, that's how what the way life is. Yeah.
What about nurses then?
Yeah, too. That's what I mean. Like but the nurses never had to taste the urine. See, never had to. Okay, maybe in some parts of the world.
They had to do what they had to do.
Some nurses in parts of the world they are doing doctor jobs actually.
Yeah.
Some nurses they are doing surgeries because it's called. Some pharmacists are actually doing doctor jobs. Some pharmacists you would go to them and tell them, I'm feeling this. They give you the medication. They're not supposed to, but that's just the way it is. People, you know. So the hereditary disease in which cells make chloride pumps but fail to install them in the plasma membrane. So chloride pumps fail to create adequate saline layer on the cell surface. So the thick mucus plugs pancreatic ducts and the respiratory duct. So there will be an excessive generation of thick mucus due to the failure to create adequate saline layer on the cell surface. So this thick mucus plugs the pancreatic ducts and the respiratory tract. And there's inadequate digestion of nutrients and absorption of oxygen. So there are chronic respiratory infections. There are chronic respiratory infections that are caused due to cystic fibrosis and excessive mucus on the surface of respiratory tracts. So the mean life expectancy, unfortunately, for patients with cystic fibrosis is 44 years old. Then there's flagellum. So now we know the difference between microvilli and cilia. Now it's time to talk about flagellum. What is a microvilli? What have we learned about microvilli? The two things we learned about microvilli. So yes, surface area increase, excellent, and they have microfilament, excellent. What about cilia? Yeah, they are for movement and microtubule. They have also an axoneme. Remember the axoneme, 9+2, the axoneme structure. So they can ask you where can you find the dining arms and the axoneme that is on the microfilament or the microtubule on the flagellum or the cilia. So what are you going to do? It's the cilia. So flagellum, they are whip-like structures. So that makes sense. We see a lot of them in the sperms because the sperm uses whip-like movement in order to propel itself and move. So the tail of a sperm is the only functional flagellum in humans. So humans do not have flagellum. It's only the males that have it to propel the movement. So it's a whip-like structure with axoneme identical to the cilium. So the flagellum does have an axoneme just like the cilium, and it is much longer than the cilium. It is stiffened by coarse fibers that support the tail. The movement is undulating, snake-like, and a corkscrew. So no power stroke and recovery stroke. It's just a stiffened movement. Okay. Then we have pseudopods. Pseudopods are different. Pseudopods are continually changing extensions of the cell that vary in the shape and the size. And they can be used for cellular locomotion, capturing foreign particles. So these pseudopods are used. That movement, we see it a lot. Look at bee. Bee looks very interesting. Where have we seen bee before? Who does bee? That kind of movement. Macrophages, excellent. So they engulf, and they imbibe, imbibe. They engulf and they imbibe material to the inside of the cell, foreign, negative, and toxic material. Now we are into the permeability. We have discussed that in the past. We have discussed that in a selectively permeable membrane, what are the factors that drive the movement? So the plasma membrane and organelle membranes are selectively permeable. So that means the membrane of the cell, the plasma membrane, is selectively permeable, meaning that it's differentially permeable, does not allow anybody to get in, does not allow anyone to go out. So it selects who can enter, who can exit. And that's not just for the plasma membrane, that's also for the organelle. So the nucleus also has a selectively permeable membrane. The Golgi body, selectively permeable membrane. The rough endoplasmic reticulum, selectively permeable membrane. Who would like to tell me the difference between proteins synthesized on the rough endoplasmic reticulum ribosomes and proteins synthesized on the free-floating ribosomes? Yes.
The one on the rough ER are creating proteins to leave the cell, and the free ribosomes are creating proteins to stay in.
Yeah, to be utilized by the cell. Excellent. Okay. So to allowing some things through, but preventing others from passing. So now let's talk about the difference between passive mechanisms that require no ATP. A passive mechanism does not require energy in the form of ATP, but obviously it does require energy in some other forms, like energy in the random molecular motion of the particles, known as your kinetic energy, and energy for filtration, diffusion, and osmosis. What is filtration? Filtration is the energy that powers the movement of molecules based on a pump. So for example, the heart. The heart pumps your blood, and the blood runs through the blood vessels till it gets into the capillary. When it gets into the capillary, then the blood starts to exit the capillary. That's much better than soda. I've recently gotten into this movement. The movement of drinking water. Yeah. You know, people carry water bottles. I used to carry soda. Yeah. Yeah. And then Gatorade. Then I hopped on the Gatorade movement. And then water, and then I'm pretty sure in a few days I'll go back to soda again.
You know what? I can't do that. It's a movement. It's a movement. And you got to
Yeah. I hope I do. I hope I can.
add some lemon to it.
I really hope. So if we have the heart, and the heart pumps blood into the aorta, and the aorta gets the blood into the capillary, and then the negative blood comes back to the right heart. So the capillaries are fenestrations. The capillaries are fenestrations. They're like holes. They have holes in them. These holes, now, do you guys see the pump of the heart pumping blood, and that's what squeezes blood to filter out. So filtration is based on, it's like when you squeeze a sponge and the water filters out from the sponge into and exits, or when the heart, you pump the blood and then it reaches the capillary, then it filters out. So filtration is based on hydrostatic pressure. Now, diffusion is not based on hydrostatic pressure. Diffusion is based on what? What is diffusion based on? Diffusion is based on, remember when I said 500 millimoles of glucose and 100 millimoles of glucose, and I make a selectively permeable membrane to glucose. What happens is the 500 move to 100 based on the collision of these 500. They are bumping to each other. They're bumping to each other, and that's what's leading the movement to happen. But in osmosis, you have water moving from an area of a higher, no, from an area of a gradient. Yeah, excellent gradient. From an area of a lower solute concentration to an area of a higher solute concentration, so it can achieve its versatile property. So it's all that's very electronegative could bind the H that's very electropositive, and then it can dissolve. It can dissolve all of the other salts. So in order for that to happen, that's known as osmosis, and as more osmotic pressure is required for that. We will talk more about this. Then there's active mechanism. Now, active mechanism is not based on hydrostatic pressure. Active mechanism is not based on no kinetic energy molecules bumping to each other. And active mechanism is not based on water movement from an area of a lower solute concentration to an area of a higher solute concentration. We're not talking about that. We're talking about we need a special type of energy. Secondary active transport is dependent on energy in the form of chemical, ATP. So now that is used for uphill gradient. So if I want to go uphill, that means I have a lot of sodium on the outside. I have a lot of sodium on the outside. This is my membrane. I have a lot of sodium on the outside. I have a lot of sodium on the outside. And I have a little bit of sodium. I have a lot of sodium outside. I have a little bit of sodium on the inside. Now what happens is there is a channel known as the sodium potassium ATPase. The sodium potassium ATPase, what it does is, and I think there's a question on the exam about that, the sodium potassium ATPase does the opposite. Usually, what's supposed to be, so we know that there is a lot of sodium outside, a little bit of sodium inside. A lot of potassium inside, a little bit of potassium outside. So we know that the natural movement, the natural electrochemical, is two gradients here, not one. Chemical, because sodium is a chemical. There is 500 millimoles of sodium outside. Want to get in to equilibrate with the 100 millimole of sodium inside. We have 500 millimoles of potassium inside that want to go out to the 100 millimoles of potassium outside. Okay? Are we clear?
Yeah.
Then we have positive charge that is more electropositive outside. Want to get inside where there is less electropositive, and there is more electropositive inside. Want to go out to the more electropositive. So the natural movement for sodium to move down. The natural movement is for sodium to move down. This is outside, from outside to inside, and for sodium to move from inside to outside, inside to outside. Okay? Okay? That's the natural movement. That movement, does it require ATP? Does it require energy? No. No, because it's natural. You're going from 500 to 100. That's the.
What about potassium?
But yeah, because there's a lot of potassium, 500 inside, 100 outside. So the natural movement is to move outside. The natural movement is just like this. When I did 500 millimole or 100, they would equilibrate at 300. Remember? That's the same thing.
That's passive.
That's passive. Because 500 to 100, there's a disparity in the electrochemical gradient. For that one, I already have my diffusion, what powers diffusion? What kind of energy powers diffusion? Yeah, the kinetic energy. So now based on kinetic energy, we move down. or electric energy. There's more electropositive electric charges outside than inside. So the natural movement is to flow in these two directions. Does it require ATP for that? No, it just requires another form of energy. Now, what does sodium potassium ATPase do? This is really important. Sodium potassium will take, and they will ask you how many. Take three sodium, one, two, three sodiums from inside where there is a little and send it back where there is a lot. So imagine you have 500 people. You open the door, it makes sense, they all get in. But imagine there's somebody very big here, and that person is able to, three people go in, get the three people, push them again, it's the 500 who are trying to get in. Like, you know, Black Friday, when the people want to run in the store, imagine somebody inside pushing that. That's exactly what sodium potassium ATPase does. All the sodium trying to get in, if you leak, the sodium will take it, throw it out. Potassium, fuel will leak out, the sodium will grab it, throw it back in. So it will take three sodium from inside where there is little, throw it out. And it will take two potassium where there is a lot outside, throw it back in. Where there is a little outside, throw it back in. So it's working in the opposite direction. It's going uphill, it's no longer downhill. You see, it's going uphill. So the movement is not like diffusion, it's going uphill. So there has to be a reason. Listen, I promise you, in life, everything has a reason. Nothing happens for no reason. So the sodium potassium ATPase is doing that, and it's consuming energy to do that. What's the reason behind all this? Homeostasis? So elaborate on that. How are we going to achieve homeostasis? By ensuring that we don't have equilibrium. Yeah.
Do you want me to elaborate?
Elaborate on your answer. So how can the sodium potassium ATPase achieve homeostasis?
Because it's not allowing the sodium to rush into the cell, so it's maintaining that balance. So
actually, it's not maintaining a balance because sodium outside is 500, and inside is 10.
That's the balance that we need to achieve. So that's the homeostasis.
If the sodium potassium weren't there, we're gonna get to 300. That's natural because remember, it flows down gradient. We're gonna have 300 sodium inside. We're gonna have 300 potassium outside. But the sodium potassium is preventing that. It's ensuring that outside sodium remains like that. Inside sodium remains. Why does it insist on doing that? Okay. It just ensure no, it's working uphill. It's ensuring the opposite. Okay, let me tell you why. A dead person, if you take a dead person's sample of the outside solution, the inside solution, I promise you, they both will be equilibrium. Because the sodium potassium ATP is not working. So now all of these guys move in through diffusion. But sodium potassium ATPase is fighting diffusion. Let me tell you why. We will see that in the action potential. So when there's action potential happens by sodium influx. So sodium will influx to the inside. There's sodium influx, and there is the sodium influx causes depolarization when the channels, separate channels, called sodium channels open. Now imagine you had no gradient like that. You didn't have 500, 100. They were equal, 300, 300. Now when these sodium channels open, are you going to have any movement? You're never going to have, because movement only happens from an area of a higher concentration to an area of a lower concentration. So the sodium potassium ATPase is ensuring that there is a disparity, so that when there is an action potential, and you know that's how we communicate. Action potential is how we move. Action potential is how we think. Action potential is how our heart beats. Action potential is how our glands secrete their their hormones. Action potential is how we go from an input. Remember we had an input, integrator, output. Those two are action potential. The sensation, remember we said the mechanical sensation leads to opening of channels. And then the ions flow in from where area of higher to lower. When we smell, that we sense the smell receptors, the chemoreceptors, the ions open and ions move from area of a higher to a lower concentration. But imagine you had no sodium potassium ATPase. If you stimulate them and they open, you will never have depolarization because you were already at equilibrium. So it will ensure there is no equilibrium so that when we need the influx to happen, the channels will open and then the channels will, then the ions will flow in. Make sense?
So it purposefully creates an imbalance.
Yes.
So it could be balanced.
Yeah, and so it can be used temporarily. So it can be used temporarily to propagate an action potential that we could use for input signal, output signal. But when everything is done, then everything returns back to a disparity, So it ensures there is a constant disequilibrium so that later on, when we need an action potential, that flow, that influx, you're never going to have an influx unless you had an area of a higher to lower. You're never going to have an efflux unless you had an area from a higher to lower. So it ensures that disparity in the ions so that when I need the influx to happen based on my stimulation, all my stimulation, whether mechanoreceptor, whether sensor receptor, whether chemoreceptor, whether osmoreceptor, whether olfaction, those smelling a scent, these scent receptors, they're all based on opening of a channel. Yes.
So does it act like a blocker until the effect is needed?
It doesn't act like a blocker. It acts like a creator of a gradient. It creates the gradient. So you see 510, that's a big gradient. That's a big slippery slide. But if it wasn't there, then the 500 now is going to become like this guy. It's going to become like this. And now they all will equilibrate. 500 and 100, they will equilibrate to 300, 300. Now when the action potential comes, you're not going to have nobody influxing or anybody. If we haven't done the action potential yet, that's fine. When we get to it, it'll make more sense. But for now, all you need to understand is that we propagate sensation, sensory input, motor output based on action potential. And action potential cause depolarizations and repolarizations and depolarizations and repolarizations in the cell membrane. So the depolarizations are caused by influx of sodium. Repolarization are caused by efflux of potassium. We're not going into the details, but what you need to know for now is that we use the movement of these ions from an area of a higher gradient outside to inside or from inside to outside to propagate an input signal or an output signal or an integration. But that movement can never happen unless you have a gradient. So the sodium potassium ATPase creates a sodium gradient that is more on the outside than inside and creates a potassium gradient that is more on the inside than the outside. Okay? Any questions? Does it make sense? Yeah, the purpose is to propagate. The purpose is to propagate. I told you that our input sensation and our output are based on action potentials. That's the law. That's how it is. We learned last week that we go from a sensor to a sensory stimulus to a sensor detector. Then you have an input signal. Then from an input signal, you go to an integrator. Then from an integrator, you have your output signal. Then from an output signal, you have an effector. Then the effector will mediate the effect. All these steps are mediated by action potentials. So the fact that we haven't studied yet the action potential makes it look like, why is this disparity there? But I'm telling you, Just for now, understand that all of this communication is based on the action potential, and the action potential, without going into detail, the action potential is based on depolarizations of membrane electric potential and repolarization of membrane electric potential. And the depolarization of the electric potential and the repolarization of the electric potential are both based on ions, because electric, so we're dealing with electrolytes. And these electrolytes, they depolarize the membranes and repolarize the membrane with their movement. So when sodium moves in, it makes the membrane, when sodium influx from outside to inside, it causes a depolarization of the membrane, making the membrane potential more electropositive. When potassium moves outside the membrane, that causes hyperpolarization, and due to the efflux of potassium outside the cell. But anyways, whether we need depolarization, whether we need hyperpolarization, we need a gradient for that repolarization to happen, for that efflux to happen. We need a gradient for that influx to happen. And that gradient will never happen unless there is it's a gradient, it's an inequality, it's a disparity. So I must have a ready disparity, so when the signal comes, I open the channel, they flow in. And that's how I get my communication. Okay?
The gradient is there to stimulate that action potential.
Yeah. So when the action potential is mediated and facilitated by the influx and outflux of these electrolytes, by the influx of sodium and the influx of potassium. But you're never going to have an influx unless you had more on the outside than inside. You're never going to have an efflux unless you had more on the inside than the outside. And you're never going to have that inequality unless you have a sodium potassium ATPase, when because these guys, if you leave them alone, they're going to equilibrate 300, 300. But that's why the sodium potassium ATPase is working, to throw them back to ensure there is always 500 outside and 100 inside. So that when the action potential comes, you open, then these guys move in.
So this is ATP that's just being used all the time, no matter what, to keep that gradient.
Yes, exactly. Yeah.
The gradient doesn't start the process. The gradient is there when the process is needed.
Excellent.
Facilitates the process.
Yes, yes, yes.
Can you give an example
Please.
when like depolarization would be needed?
Okay, so the process of the action potential is how we communicate an input signal and an output signal. Let's say when we're dealing with hyperthermia or hypothermia, the signal that there is a high increase or a low or a depression in the temperature, or high glycemic index, too much sugar or too low sugar, all of that signal that goes from the sensor to your integrator who will repair the problem is mediated by an action potential. So that route going from your finger, from your thermoreceptors on your skin, saying that it's too hot, to the hypothalamus, in the thermal nucleus of the hypothalamus, and the hypothalamus sending another action potential to your sweat gland. That route is all by action potential. So that route is not stimulated when you are cold, not stimulated when you need to secrete testosterone, or when you need to secrete glucose or insulin. Only the route that you need to repair homeostasis is mediated with action potentials. That's the only way the communication happens. You understand?
I understand action potential. It's just the depolarization. What's the purpose?
Okay, so the depolarization is how the action potential happens.
Yeah, that's what I'm saying.
Okay,
If you're
yeah, we're not going into the details of the depolarization. All that we need to know for now is that we have a lot of sodium outside and we keep it that way. We have a lot of potassium inside and we keep it that way. So now you guys want to go into the details of how the action potential would happen. We will get to that. But we're not talking about that now. Now all we need to know is that there's something called an action potential, which is the signal that is being mediated from the sensor to the effector. That's the input signal, from the effector to the integrator, from the integrator to the effector, and so on and so forth. That signal happens through, that communication happens through electrical communication known as the action potential. And the action potential happens when there is an influx of sodium from an area of a high concentration to an area of a low concentration. And it is mediated, actually not just, this is called depolarization. When sodium comes in, that's depolarization. So the action potential is actually two steps. There's a depolarization, increase in membrane potential. Then there is a repolarization, decrease in membrane potential. Increase in membrane potential, decrease in membrane potential. So when the increase in membrane potential, that means the sodium is influxing. When that means the sodium is influxing. When there is a drop in action potential, that means the potassium is effluxing, getting out. Potassium is effluxing. And this is the membrane potential. That's the membrane potential, and that's the time in milliseconds. So as time goes on, you have a series of depolarization, repolarization. That's an action potential. A depolarization plus repolarization. That happens when these guys, when the sodium influx and potassium efflux. That's how the signal gets to, from the sensor to the integrator, from the integrator to the effector. That's how the signal passes through the depolarization. But we're going to get to that. We're not dealing with depolarization. We're now just dealing with appreciating that this sodium potassium ATPase has two seats for potassium, and it has 3 seats for sodium. When sodium naturally moves in down electrochemical gradient, it will throw them out. The 3 of them will go out. And when these two potassiums when the 2 potassium leak out, it will throw them back in. It will keep that disparity, that inequality. So when we need an action potential, then other channels can have their influx of sodium so that the depolarization can go up, and they can have their efflux of potassium so the depolarization, so the action potential now can repolarize. You understand?
So like the effluxes and refluxes would happen when like the action potential is needed.
Yeah. Yeah. So exactly. So now let's say I have a communication between my sensor, like my skin, to my integrator. So this will be going like that till we get to the integrator. Then from the integrator, we're going to be action potential to the effector. Then from the effector, we're going to have the mediate the effect. Then we stop. Then all of this returns back to normal like that, like before. Okay? Yeah. Just for now, understand that sodium potassium ATPase creates a disparity, creates a gradient, creates an imbalance that we will later on use to generate our action potential when it's needed. Okay? So the sodium potassium ATPase has 5 regions, 3 for sodium, to move sodium after it flows in, send it back out to make sure there is no balance, and take the potassium that escaped outside, down concentration gradient, return it against concentration gradient uphill, and ensure that there's always a disparity. And in expense, it will use ATP for that. So that's why they call it secondary active. This is active transport. This is active transport, and it uses ATP. So we convert ATP to ADP. Okay. All right. So now let's look at active mechanisms consume ATP, like active transport and vesicular transport. So the carrier-mediated mechanisms use a membrane protein to transport substances across the membrane. We talked about filtration, and that filtration particles are driven through membrane by physical pressure. So an example is filtration of water and small solutes through gaps between cells or filtration pores in the capillary walls. And that allows the delivery of water and nutrients to the tissue. So it is always powered by hydrostatic pressure. So we just use it to push solutes from one area to the other. We use it to deliver good things like oxygen, water, and nutrients to tissue, and also to the removal of carbon dioxide and waste. There we go. That's filtration. We see blood pressure in the capillary. Like I told you, every picture, make sure you understand it really well, every figure. So the blood pressure in the capillary forces water and small solutes, such as salts, through the narrow clefts between the capillary beds. So in simple diffusion, the net movement of particles from a place of high concentration to a place of lower concentration, from a place of a higher concentration to a place of a lower concentration. That is due to constant spontaneous molecular motion. We talked about that, the kinetic energy. And the molecules collide and bounce off of each other. So substances diffuse down concentration gradient. And the concentration gradient, sometimes there's heat gradient, sometimes there's thermal gradient, sometimes there's pressure gradient. So from an area of a higher concentration to an area of a lower concentration. And that occurs in air, and water does not require a membrane. So the substance can diffuse through a membrane if the membrane is permeable to the substance. If it's impermeable, even if there is a gradient, you cannot be able to move. So we talked about, okay, so now we're going to talk about the factors that affect diffusion. Obviously, the temperature. So the more you heat up the solution, the faster the molecules are going to be moving due to them bumping to each other more and more, and then that is going to lead to power their movements to cross that permeability, that differential membrane. Then the molecular weight. Obviously, the larger molecules move slower, and the smaller molecules move faster. So if you had a solute of really tiny, particles like sodium chloride, they will move and diffuse down concentration gradient faster than really big molecules like glucose and protein. Also, the steepness of the concentration gradient. If you had a concentration gradient like 500 to 100 compared to 700 to 100, then 900 to 100, then that's a steeper gradient. The more the absolute disparity between the gradients, the faster the diffusion will be. The membrane surface area. So the higher the surface area, that's why we have the microvilli, because when you increase the surface area, you maximize the rate of diffusion. So that's a simple factor. That's actually very important. And membrane permeability. The more permeable you are, the more pores you have, the more solutes are going to be able to diffuse. Okay? Osmosis is the net flow of water through a selectively permeable membrane. And water moves from an area of a higher water and lower solute to an area of higher solute, lower water. So water can diffuse through the phospholipid membrane, but osmosis is enhanced by aquaporins. So obviously water is polar, but it is so small, it can even flow through fats. It can even flow through lipids. And the problem is, those lipids, obviously they are non-polar, so they would impede the movement of water through them, but they will not stop it completely. Like if you have a barrier made of lipids, complete lipids, and you pour water on top of it, will water not leak through? It will. But let's say you wanted to move faster, then our cell membrane has aquaporins. These aquaporins, they are transmembrane, obviously, and they would open to allow for water to move through. Okay? So these are aquaporins. They would accelerate the rate of movement of water down the plasma membrane. So cells can speed osmosis by installing more aquaporins. So if we need more water there will be transcription in the DNA to give me mRNA, that when I translate the mRNA, I get structural protein like aquaporin and then plug those in. The same way insulin will cause the generation of GLUTs. Remember the GLUTs, glucose transporters, and we plug them in the membrane, and then glucose will be able to flow. Glucose will be able to flow inside the cell. So the cell can transcribe, translate, and make these channels and plug them on and off whenever it needs to. So it's not like they are there forever. So they are put in there and removed as needed by the cell. Okay, so what do we have here? If we look at this diagram, we see side A and side B both have the same water level. You see? So the issue wasn't in the water. But here you have more solute. Here you have orange, and here you have no orange solute. Then you make the membrane permeable to who? The solute or water? Water. Then water will move from an area of a lower solute, no orange, to an area of a higher solute, orange. And that will represent for us the process of versatile solvent due to a high osmotic pressure. So there is low hydrostatic pressure. The water did not move based on a pump or some force pushing the water. The water moved based on osmotic pressure. Osmotic pressure is like a driving force to go and dilute these really solutes. Okay. Osmotic pressure. So osmotic pressure is hydrostatic pressure required to stop osmosis. Is the hydrostatic pressure required to stop osmosis? Increases as the amount of non-permeating solute rises. So the more solute that is non-permeating, cannot cross, the more you add here, the more the osmotic pressure and the more water is going to cross. Non-permeating solutes cannot pass through the membrane like proteins. Hydrostatic pressure is the fluid pressure on the membrane. And reverse osmosis is the process of applying mechanical pressure to override the osmotic pressure. Okay. So osmolarity is the osmotic concentration, the quantity of the non-permeating solutes per liter of solution. So the body fluids contain a mix of many chemicals, and osmolarity is the total osmotic concentration. It is 300 milliosmoles per liter. So the same way we have hyperthermia, hypothermia, we have hyperosmolarity, hypoosmolarity. And we don't need hyperosmolarity, we don't need hypoosmolarity, we need eusmolarity. So tonicity. Tonicity is the ability of a surrounding solution to affect the fluid volume and pressure in a cell. So now a solution, you know that the cell membrane is permeable to water. If we need it to be more permeable, we'll plug in more aquaporins, but otherwise we don't need. So that means if you drop a red blood cell in a really hyper concentrated solution, what's going to happen? What is going to flow from the red blood cell into the solution? Because the solution is really, really hyperosmotic. So if you drop a red blood cell, if you have three solutions, one solution, the osmolarity is really high. One solution, the osmolarity is equal to the red blood cell. And one solution, the osmolarity is really low than the red blood cell. So here, when the osmolarity is so high, water moves from an area of, here the osmolarity of the red blood cell is low, the solution you dip the red blood cell is high. What's going to happen is water is going to flow out from an area of a low solution to an area of a higher solution, right? And that's going to cause the red blood cell to shrink inside. Then when they are both equal, water going outside and water going inside are both equal. And lastly, if the solution is hypoosmotic, what's going to happen when the solution is hypoosmotic and the red blood cell is hyperosmotic, water is going to flow from the solution into the cell, then the water is going to swell until it bursts. So the solution that is really osmotic is known as hyperosmotic or hypertonic. Equal isoosmotic or isotonic. Really low in osmolarity, that is hypoosmotic and hypotonic. Hypotonic. Okay, there we go. Tonicity is the ability of a surrounding solution to affect the fluid volume and pressure in a cell. It depends on the concentration of non-permeating solutes. If a solute is more concentrated on one side of the membrane, it causes osmosis. Okay, let's look at the different. You need to know those difference, those three. I didn't have it on the lab exam. I erased this one as well because it's just so basic. But everybody must understand it. Like hypotonic solution causes the cell to absorb water, swell, and possibly burst. And it has a lower concentration. And then hyperosmotic is going to cause the water to shrivel. Isotonic, it will be the same. You see, that's a hypotonic. The water in a hypotonic solution is going to swell like that. In isotonic, it's going to look just normal. And in hypertonic, it's going to shrink. So you need to know how the red blood cell looks like inside the, you see, that's hypotonic, that's isotonic, and that's shrinking hypertonic. Now, this is the carrier-mediated transport. The carrier-mediated transport of proteins, the carriers in a cell membrane carry solutes into or out of the cell. The carriers exhibit specificity for their particular for their particular solute. So the solute here is my ligand. So it binds to a receptor site on the carrier protein, and the solute is released unchanged on other side of the membrane. But the problem is carriers are proteins, and they have a transport maximum. We talked about this in glucose transporters in the kidney. So if a patient has sugar or glucose in their urine, that means in the kidney, the transporters of glucose have achieved their transport maximum. They are overwhelmed. There are so many solutes. So that is known as the transport maximum. This concept is very important. So you see here the rate of the solute transport. What happens is the more you add, the more solute you add, the more concentration of solute that you add, the faster the rate of the reaction going to be going. The more solutes you add, the more rate of the reaction is going to go. Until you put too much, until you put a lot more than the transporters can handle, and that will be achieved at the transport maximum. There are three kinds of carrier proteins. There are the uniports. Uniports are like a calcium pump. These are carriers that move one type of solute, either down concentration, always down concentration gradient. A symport is a carrier that moves two or more solutes in the same direction. It's symport, meaning they either move them both downhill or move them both from outside to inside or move them both from inside to outside. But in the end, is always going to be down concentration gradient. No matter if you're using a uniport or a symport or an antiport, the antiport uses one direct, throws one outside and one the other direction, like a sodium potassium ATPase. Sodium potassium ATPase takes how many sodium and how many potassium and in which direction?
Sodium influxes into potassium.
Nope. Yes.
Sodium going in, higher concentration.
the sodium potassium ATPase will what does the sodium potassium ATPase do?
It comes outside.
It pushes out,
It pushes who and how many?
pushes out the sodium.
Three sodiums outside and potassium, how many? Inside. Yeah. So it moves three sodium ions outside against concentration gradient and two potassium to the inside against concentration gradient. So that makes it an antiport. It's an antiport. And a symport drives both in the same direction, like a sodium glucose transporter. So the three mechanisms, these are the three mechanisms of these are carrier mediated. Some of them require ATP, others require just a gradient. So the three mechanisms of carrier mediated transport. So facilitated diffusion, primary active transport, and secondary, there's secondary active transport. So now, the facilitated diffusion is when you have movement down concentration gradient, but the solute you're moving is polar. It cannot dissolve in the lipid bilayer. Like for example, the glute. The glute is a perfect example for facilitated diffusion because it facilitates the movement of glucose down concentration gradient from the outside in the blood to inside of the cells of the liver, and it moves it down concentration gradient, and it allows for it to be carried to the inside because glucose is sugar, is polar, and it cannot dissolve, so it goes through the glute carrier, and it does not consume ATP because that is still facilitated diffusion. Then there is primary active transport, like the sodium potassium ATPase. That is when you use energy in the form of ATP. When you use ATP to throw three sodiums outside and potassium to throw two potassium inside. So the carrier protein uses ATP for energy. Calcium would be the calcium pump uniport. It uses ATP while expelling calcium from cell to where it's already more concentrated. And so I gave you an example of the sodium potassium ATPase, but that's not the only one. There is also a calcium ATPase. It takes ATP to throw calcium against concentration gradient, not down concentration gradient. So primary active, because there's questions on the exam about the difference between facilitated diffusion, primary active transport, and secondary active transport. You see, this is facilitated diffusion. In facilitated diffusion, do you see any ATP? You just have a lot outside that are flowing inside. So a solute particle enters the channel of a membrane protein carrier. Then you have the solute binds to a receptor site on the carrier, and the carrier changes the conformation. The carrier changes the conformation. So that shows you the process of facilitating the diffusion. So we need a carrier that allows for the passage. So this red solute, why doesn't it just go through? Because you know all you need is a down concentration gradient. There is a lot outside, a little bit inside. Why don't the red go through the yellow? I'm sorry? Yeah, so what is the reason? Somebody please give me the answer in full, complete sentence. Why can't the red solutes move down concentration gradient without a carrier, without this purple carrier? Why can't they just go through the yellow if all you need is more on the outside than the inside? If all you need is a gradient, and the gradient is right there, there's a lot of red outside, a little bit of red inside. Why do I need purple carrier? Why can't they just move in? Yes. Give me a complete sentence. Yeah. Describe to me. Don't just tell me because it's hydrophilic. What is hydrophilic?
It outside is the protein is lipo
The protein? The protein? What protein?
The one that facilitates the passage.
Yeah, okay, good. So now that's the carrier, the membrane carrier. Okay, so the membrane carrier is lipophilic. Okay, what is the question? I'm going to say the question. Please understand the question so you don't answer some other question. The question is, if the reason why we diffuse is we need a gradient, 500 on one side, 100 on the other side. So here, there is a lot of red outside, a little bit of red inside. So obviously, we're going to move from outside to inside. But why we need this purple carrier? Why can't they just move like through the yellow? Why can't the red dots, the red many dots, go through the yellow? Why do they need that purple? Yes.
So it's not permeable to the membrane without the channel because it's like lipophobic.
Because the solute that's red is lipophobic hydrophilic. Good. So that we need the carrier. A perfect example of that is what? Somebody that needs a facilitator to move, a carrier to move them down concentration gradient. Epinephrine? Do we need epinephrine to move down the cell? Epinephrine binds the receptor outside, and then a signal transduction cascade with cyclic AMP and kinase happen. That's not what's happening here. There is no cyclic AMP here. Here we're just flowing down. Glucose is so polar outside, and even though it's a lot outside, like insulin, this is a perfect example of a GLUT of insulin transporter. For GLUT, this purple is GLUT, and that's red could be glucose. So now you have a lot of glucose, but it's polar. It cannot go through the yellow lipid, the yellow butter, the yellow lipid, so it can go through that purple passage, that tunnel. And it is not just like the carrier is not just like a tunnel. You just go through it. No, it's actually, it makes a conformational change. It bind, it changes structure, then move you in, then return. It's not just like a hole that you go through. The aquaporin is like a hole. But those facilitate, that's why it's a facilitator. They are carrier, they carry, they literally carry. The answer is that those red ones are hydrophilic, lipophobic. They cannot cross the yellow because that's lipophilic and hydrophobic. So they need a mediator to carry them and let them admit them in. Okay? Secondary active transport. The carrier moves solute through the membrane but only uses ATP indirectly. Now that's the important one. So not only we have primary active transport, we have secondary active transport. Well, the fact that is active, it means it's not just concentration gradient, is not just down gradient. It says that we need energy, but if it's ATP, that makes it primary active transport. But it's secondary. That means we don't use ATP, but we got to use something else. What are we going to use? We use ATP indirectly, like the sodium glucose transporter. So what happens here? That's really important. What happens here is in the cell, sodium is a lot outside. We talked about that already. And I want to move glucose in. That's a separate transporter. It's called the SIGLIT, sodium glucose transporter. What it does is it uses the movement of the natural movement of sodium from an area of a higher concentration to an area of a lower concentration to spin the movement of glucose from an area of a higher concentration to an area of a lower concentration. Like in the waterfall, the water is moving, rotating the blades, and the blades are spinning, and then there's copper wires and copper electric wires, and they're spinning with magnet called electromagnetic field. We get energy. Here we shuttle, we hitch a hike. So sodium is already moving down concentration gradient. It's not a secret that there's a lot of sodium outside. little bit of sodium inside. So the sodium moves in. But while it's moving in, the singlet will cause the sodium to move down and use the energy of sodium moving down to move with it glucose. It's like when you're going to Manhattan and you hitchhike somebody with you. So he's already going there. You're already going there. You just take that person with you. Sometimes it works in the opposite direction. Sometimes sodium is more, so you can have this secondary active transport where sodium moves in and somebody else move in with sodium. They discovered also you can have sodium move in and you throw somebody out. It can happen. So they don't have to be in the same direction. But we rely on sodium. And we rely on sodium because of the sodium potassium ATPase. I'll show you now in a better illustration. So let's look at secondary active transport. Secondary active transport carrier moves the cell through the membrane, but uses ATP indirectly. It moves glucose into the cell. You see that's the singlet. That is our sodium glucose transporter. There's a lot of glucose outside and a lot of sodium outside. So sodium moves in from a lot of outside to the inside. And the sodium, that's on the apical surface. That's on the apical surface. Look at the other surface. At the other surface, you have the sodium potassium ATPase using ATP to throw out sodium. So it's always creating a gradient. So no matter how much sodium flows in, the ATPase will throw it out. You guys see? So here, there's a lot of sodium outside. It moves in with glucose. You see, sodium moves in, glucose moves with it. But when the sodium moves in, it's going to accumulate here. There's going to be a lot of sodium here. What's going to happen now is the sodium potassium ATPase will throw the sodium against concentration gradient on the other side. So that's the front yard, that's the backyard. But it doesn't matter whether front yard or backyard. Sodium is still always a lot outside. So here sodium is a lot, moves down, hitchhiking with it glucose. And when it gets here, sodium potassium ATPase removes it, throw it against concentration gradient back outside, and then depletes it from here. So here you see that we use primary active transport to create a gradient for secondary active transport. Okay? We use the sodium potassium ATPase to remove sodium from the inside to the outside. And when we deplete sodium from the inside to the outside, 3 sodiums outside, 2 potassium inside, so there is less sodium inside. What happens now is sodium will move down concentration gradient, hitchhiking with it glucose. And then the sodium potassium ATPase. 3 sodium outside where there is a lot, you see a lot of sodium, a lot of orange sodium. So a lot of sodium goes outside and a lot of sodium is thrown outside against concentration gradient. And the blue here is potassium and 2 are thrown in concentration gradient. Okay, this just shows us how phagocytosis happened. We talked about this on the first day of class, where you have a phagocytic cell encounters a particle of foreign matter, and then the pseudopods will go surrounding it, engulfing it, phagocytosing it, then fusing a lysosome with this phagosome that was indosed. Then you have a phagolysosome. Then you have them now secreted out as edible blebs that are harmless. And then we have receptor-mediated endocytosis, where there's a receptor on the outside. Once you bind to it, you will be imbibed and you will be brought in with a vesicle to the inside of the cell. You see, this is called a clathrin-coated pit. So the more you bind, a hole is, you see, this was the membrane normally. When you bind the receptor, a hole is going to be made like that. And You're gonna make a vesicle that's called a clathrin coated vesicle, and then that vesicle is endocytosed. Transcytosis is movement across the cell by capturing it on one side and releasing it on the other. And exocytosis is the discharge. So endocytosis, bringing material in the cell. Exocytosis, throwing material outside the cell. And transcytosis is going through the gaps between the cells. Exocytosis, we throw out the content from the inside. You see here, here we had a bubble inside that we threw it outside. Now it open and all the content that was inside the bubble is going to be thrown outside. That's exo. So now we are exiting the solute out. Okay. And the cytoskeleton, we talked about the microfilaments and the microtubules. And we've seen that the microtubules are found in the cilia and the microfilaments are found in the microvilli. And these are the nucleus, and they have multiple, so we've talked about how the cell membrane is permeable to is selectively permeable, not just the cell membrane, but also the membrane of the nucleus and the membrane of the mitochondria and the membrane of the other organelles. Okay, that's the structure of the nucleus. We talked about the rough endoplasmic reticulum, the smooth. So the rough endoplasmic reticulum has all of these ribosomes to make protein that will be exported out the cell. And the smooth endoplasmic reticulum is important for detoxification and synthesis of lipids. Okay. That's we talked about the lysosomes. Peroxisomes are important because they are able to convert for us harmful free radicals and change them into harmless harmless substance like oxygen and hydrogen peroxide. Proteomes, they are very important for the destruction. They carry a lot of metalloproteinases, degradative enzymes, proteolytic enzymes. That's why they say proteasome. And they are the ones who will engulf and destroy the damaged proteins. The proteasomes are like, the shredder that you put paper in to shred the paper? The proteasome, you put all the misfolded damaged protein there. Oh, right here. You see the shredder? That's the proteasome. You put inside it the bad protein after you tag it with ubiquitin. Where is ubiquitin? So ubiquitin, that's the tag. That's the purple tag. They didn't name it for you. Maybe they want you to name, but the name is the ubiquitin tag. Any misfolded protein is tagged with this purple ubiquitin tag, and once it's tagged, the proteasome is going to shred it. It's going to put inside the shredder and cut it. That's the proteasome. The mitochondria is the powerhouse of the cell. It's responsible for the programmed cell death. There was a question about that. Apoptosis, programmed cell death, is mediated by mitochondria. Inclusions are like fat, lipid, vesicles, storage products, or foreign matter in the cytoplasm, and accumulated cell products. Like, they could be useful or useless, and they could also have inclusion of viruses, and they are never enclosed in a unit membrane, and they are not essential for life. They are like storage form. Yes? Proteasome? The purple thing is the proteasome? The purple, yeah, it's a tag. It's called a ubiquitin tag. They didn't name it, but okay, you can spell it how you want. Ubiquitin tag. That's important. Actually, some people. I'm sorry?
Because it's always there? Is that why?
If a protein needs to be removed, it will be, if a protein is misfolded or damaged, needs to be get ridden off, it be tagged by ubiquitin tag, that purple tag, you see? And that purple tag will cause the proteasome to shred all of the misfolded protein. Of misfolded damaged proteins. Good. All right, guys.